Hello everyone, you are welcome to the third session under Unit 3, and in this session we'll be looking at the identification of organic compounds by UV-Vis spectrophotometry. So at the end of the session you should be able to learn about ultraviolet visible absorption spectrometer, absorption spectrum. You should be able to know something about the D'Alembert law, and you should be able to gain experience into what the various scan parameters do, and then why and when to change some of these parameters when you are running your sample using the UV-Vis spectrophotometer. So first of all, we will take a brief look at the UV-Vis spectrum, the ultraviolet visible spectrum. So this is the electromagnetic spectrum comprising of radio waves, microwaves, infrared, visible, ultraviolet, the vacuum, X-rays, gamma rays, but we are more concerned about this side, the UV visible side. So ultraviolet visible, right? So between 700 nanometers to the 100 nanometers, where the ultraviolet lights and then the visible lights are. That's the range for this. Okay, so based on the D'Alembert law, UVs help us to identify how much of a species is present in a sample by running its absorption spectrum. So by using the D'Alembert law, which is absorption equals epsilon L C, where the A represents absorption, so A will represent our absorption or absorbance, epsilon will represent the molar absorptivity, L is the path length of the light, and then the C is the concentration. Now, because absorption is directly proportional to concentration, whatever absorbance we get, depending on the molar absorptivity and then the path length, the concentration can be calculated, right? So that's the D'Alembert law and how it is being applied in identifying the concentration of an analyte of interest based on the absorption or absorbance value that is obtained. Now, the UV-Vis spectroscopy involves measurements of the fraction of incident electromagnetic radiation that is either absorbed or transmitted by a sample. This has already been spoken of. And then measurements can be performed at a single wavelength or across a broad range of wavelengths when the spectrum is produced. So running your UV-Vis, right, there are cases where you can select a specific wavelength. That is, if you are sure that your analyte of interest or the analyte you are taking its absorbance has this known absorbance value within this range, say 400 nanometers, then you can set your UV-Vis wavelength at a single wavelength of 400 nanometers or 420 nanometers to run your sample. However, if you're not so sure and it's an unknown compound, then mostly we use a range of wavelength, right? So if you're not sure, then you can set the range, a broad spectrum range of say 400 to 600 nanometers. Then means you are using a broad wavelength. Now the compound can be characterized qualitatively and identified by comparing the absorption spectrum produced with the spectra of known compounds. So assuming yes, it's an unknown compound, you want to run the UV-Vis to identify it. Then the best another approach is by running your sample. You run your sample over a broad wavelength, and then wherever the sample absorbs, then you can make a comparison with known compounds that absorb in that same region. Then you can make your comparison by that to identify your unknown compound. Now, in UV-Vis spectroscopy, there's also the calibration, right? So sometimes you calibrate your instrument over time. With time, sometimes you want to calibrate it to increase its ability to reproduce accurate results. So we have the chromium glass method. Now, this chromium glass method is commonly used as a wavelength standard for the calibration of spectrophotometers. Now, this method allows you to verify the wavelength calibration at 3 different wavelengths. So you calibrate your instrument at 460 nanometers, 360.9 nanometers, and then of course 279.4. So the wavelength is spread across the UV-Vis ultraviolet visible wavelength Now, the performance is considered satisfactory if the wavelength error of the chromium glass absorption lines are within plus or minus zero point 0.3 nanometers, right? So you calibrate your instrument over time to see how good the instrument is working. Okay, so there are cases where the effects of the bandwidth can also be determined, so that you appreciate the effect of the bandwidth on the kind of results you can get. So this can be done here. You can use benzene to do that. So your sample cell can be filled with benzene, just one drop here, and then you run the spectra with this wavelength range 220 to 208 nanometers, and then you change the bandwidth from 4 to 2 to 1, 0. 0.5, 0.2, 0.2. Then you check the effects it has on the results, and then you can plot a graph to see how different or similar they are. There's also the cuvette and solvents that is also talked about. So here you can obtain spectrum of an empty quartz, and then across the maximum wavelength range of the instrument, and then you can put the quartz inside and then run it as well, and then compare the differences. Because what you usually want to say is that your sample cell or your cuvette shouldn't absorb in that region. So in the absence of the quartz cuvette and the presence of the quartz cuvette, there shouldn't be any appreciable change in the spectrum when it is run. And then you can, when you are done with that and you are sure that it's not absorbing, then you can add water to the cuvette, run it, and you can add methanol, run it, and then hexane, and then as well run it, and then see their absorbances. Okay, so with that done, this is typically going to be done in the laboratory. Afterwards, in your report, you have to look at how to sketch the basic components of the UV scanning spectrometer. You should be able to know about the kind of molecules or compounds that absorb in this um, region, or that are useful, or that should be run under the UV spectrophotometer. You have to know about the bandwidth. You should be able to label copies of all spectra and peak data. You should be able to discuss in what situations would an accurate calibration of the UVs be most important. So when do we need to calibrate the instrument for it to work very well, just so it doesn't affect the results you have? And there are quite a number of these discussion topics that you need to add to your 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 report. You should be able to compare the different optical material used to make cuvettes. So we have different types of cuvettes, and what materials are being used, and then what ranges of wavelength do these materials absorb. The list goes on and on.